Hello everyone! In this video, we will discuss a very important tool in mathematics, the Moivre's theorem. This theorem cleverly connects complex numbers with trigonometry, which is not very practical in calculations, but also reveals deeper connections in mathematical structures for us. Next, we are going to explore this theorem and its applications. So what is the Moivre theorem? It's a statement that a complex number z in a polar form can be represented in this way. It's r times cosine theta plus r sine theta. To find the nth power of the complex number, we just raise r to the n, and for the other part, we multiply the angles by n. This theorem is very useful in simplifying calculations, solving equations, and proving trigonometric identities. Before delving into the specifics, let's briefly introduce the proposer of this theorem, Abraham de Moivre. In addition to proposing this theorem, he also made significant contributions in the fields of probability theory and mathematical physics, which are still of great significance today. Let's first review the basic concepts of the complex numbers. There are three ways to represent complex numbers. First is the definition. So the complex number z in rectangular form is a plus bi, where a and b are both real numbers, and I squared is equal to -1. In the polar form, z can represent it in this way. It's r times cosine theta plus r sin theta. And we also call it trigonometric form. There is also an Euler's form. It's r times e to the power of I theta. We also call it exponential form. And we need to notice that in trigonometric form and exponential form, r is the modulus of the complex number, which is equal to the square root of a squared plus b squared. And theta is the argument of the complex number, which is the inverse tangent of b over a. So let's look, this is a and this is b. So the hypotenuse is going to be r, which is the absolute value of the complex number. And inside of that, we have the angle, theta. And we have some facts. This is a complex conjugate of a complex number. It's defined as a minus bi, and the product of them is equal to the square of their modulus. Okay, let's take a look at the formal expression of de Moivre's theorem. For any real number x and integer n, it is the case that the nth power of cosine x plus I sin x is equal to cosine nx plus I sin nx, where I is the imaginary unit. For the proof of this theorem, we can use mathematical induction to prove it. This is the basic step, where n holds for the smallest natural number 1. Next is the inductive step. We assume that this proposition is true for a certain natural number k. Then under this assumption, we need to show that it also holds for k plus 1. So when both steps are completed, by mathematical induction, we can conclude that this theorem holds for all natural numbers. However, in the statement of de Moivre's theorem, we know that n holds for all integers. So next, we need to consider when n is non-positive. It is very obvious that when n is equal to 0, both sides of the function is equal to 1. Now, we consider negative n for natural number n. From this step to this, we use the conclusion we have proved just now. And next step, we use a small conclusion. We just write z as cosine nx plus I sine nx. And we have the fact that the modulus squared is equal to z times the complex conjugate of z. And we move z to the other side and modulus to the other side. Then we have the inverse of a complex number, which is 1 over z is equal to the complex conjugate over the square of the modulus. So cosine nx plus I sine nx, its inverse is we can write as the complex conjugate cosine nx minus I sine nx over the square of the modulus. And we know that the modulus is just equal to 1. So we have this. And next, we know that cosine x is an even function, and sine x is an odd function. So we can obtain this. Now we can conclude that the result holds for all integers. Let's first take a look at the example 1. We first need to convert it into the polar form. And we know that r is equal to the square root of 1 squared plus 1 squared, which is the square root of 2. And theta is the argument of a complex number, which is pi over 4. Now we can write 1 plus I as the square root of 2 times cosine pi over 4 plus I sine pi over 4. And next, we apply the theorems. So we just raise the square root of 2 to the power of 4, and we multiply both angles by 4. Then we can get the result. The example 2 is to prove the trigonometric identity. We first associate sine 3 theta with the theorem. So we raise cosine theta plus I sine theta to the power of 3. And we just want the imaginary part. And we need to expand this. So, and next we need to eliminate the real part. And to obtain sine 3x, we need to divide both sides of the functions by I. So we have this. And we need to notice that cosine squared theta can be written as 1 minus sine squared theta. So we can prove the identities. The example 3 is a variant of the trigonometric identities. And before that, we need to know some important conclusions. We just write z as cosine theta plus I sine theta. Then the inverse of a complex number is equal to cosine theta, cosine negative theta plus I sine negative theta, which is cosine theta minus I sine theta. And when we can find that when we add both of the functions equations, we can obtain this. We just eliminate the imaginary part, I sine theta. And when we use the first function to minus the second one, we can have z minus 1 over z equal to 2I sine theta. The right is the same. Now let's solve the example 3. Express sine cubed theta in the form. Using the conclusion, we can raise z minus 1 over z to the power of 3. So we first write z minus 1 over z as 2I sine theta. Then there, to the power of 3, we have 8 times minus I times 3 cubed theta, which is negative 8 times I times sine cubed theta. And next, we need to expand this. So we can write it as z cubed minus 3 times z squared times 1 over z plus 3 times z times 1 over z squared minus 1 over z cubed. And then we just combine the terms with z cubed and combine the terms with z to the power of 1. And we use the conclusion we have just proved. It's z to the power of n minus 1 over z to the power of n is equal to 2I sine n theta. So we write the first term as 2I sine n theta, and the second term as 2I sine theta. And so we have sine cubed theta equal to 2I sine 3 theta minus 6I sine theta over negative I. Sorry. And so we can have this. And this identity is the same as the previous one. That's very interesting. Okay, beyond the Moivre theorem. The Moivre theorem plays a crucial role in mathematics, particularly in finding the roots of complex numbers. It also has a profound connection to Euler's formula, which bridges the world of trigonometry and exponential functions. In practical application, it's instrumental in Fourier analysis, founding the foundation for signal processing and wave analysis. Beyond that, it opens doors to studying complex dynamics and fractals, which are essential in understanding chaotic stiffness and intricate patterns. Taking it further, the Moivre theorem can be applied to quaternions, providing a mathematical framework for rotations in 3D space. It also allows us to define generalized powers and fractional exponents, which are vital in advanced computations. Finally, it ties to group theory, showcase the elegance and connectedness of mathematics. So in summary, in today's video, we explored the Moivre theorem, proved it using mathematical induction, and learned how it simplifies powers of complex numbers and derives trigonometry identities. Beyond that, we also discussed its broader implication and applications. For those interested in exploring further, I recommend checking out works by Stewart, Needham, and online resources like Khan Academy and Math World.